Welcome! Today we will deal with internal forces in Gerber beams, which are articulated beams. I will show you how to solve a Gerber beam using two examples. In the first example, I will solve it by breaking the Gerber beam into simple beams. And in the second example, I will do it without breaking it into simple beams. By simply calculating the beam with joints that we already receive without decomposing it into simple beams, because that too is possible. However, there are different task contents, and some tasks simply require us to decompose the Gerber beam into simple beams and then calculate it, to show that we can do it and not just solve the beam as we can, but as required. So now we will quickly move on to the second beam. Now, the second method, we have such a beam there are also 3 joints so that it isn't easier. Now we'll do the same, which is to solve it, calculate the reactions, and draw the internal force diagrams, but without breaking it into simple beams. So the principle is this. We have 3 balance equations at our disposal, the sum of projections on the axis and the sum of moments at any point. And from each joint, we have 1 additional equilibrium equation. If it were a frame, it would depend on how the joint connection looked, as one joint might yield more equations if it connected more than 2 rods. For beams, 1 joint equals 1 additional equation. This equation is the sum of moments in the joint from the right or left side, meaning if we were doing the sum of moments at this joint from the right side, we would cut off what is on the left. We do not see what is on the left side, and sum up all those forces on the right side, summing their moments about point E. So we have 3 equilibrium equations, plus 4, 5, 6, plus 3 from each joint. So we have 6 equilibrium equations. So we have, once again, the sum of moments at any point. The sum of moments in each of these 3 joints from any side we want, but assuming one joint gives 1 equation. And we also have the sum of projections on the x-axis and the sum of projections on the y-axis. From the sum of projections on the x-axis, I already entered the reaction HA as 0. And now let's consider how to sum moments precisely at this point E, meaning in joint E from the right side, we will have unknowns VF and VH. So 2 unknowns, because here it is not possible to immediately create an effective equation to calculate any reaction immediately. But if we then sum the moments in joint D from the right side, we will also have 2 unknowns, and the same ones. So we will have a system of 2 equations with 2 unknowns, so we will be able to solve it. So we have already calculated VF and VH. Next, when we calculate the sum of moments at joint B from the right side, VC will be unknown since the other 2 are already calculated. Then the sum of moments at any point, it doesn't really matter, it could be at point A. For example, from that, we will calculate the moment at point A, and the sum of projections on the y-axis, the reaction VA. And when there are more joints, it's usually the case that we need to arrive at some system of equations to calculate it. As I said, the sum of moments at point E from the right side. We could do it from the left side, but as I presented, it will be easier to calculate from the right. And then we'll sum up the moments at point D from the right side. And the system of these 2 equations will allow us to calculate the reactions VF and VH. And that's the sum of moments at point E, which is minus VF times 2 plus 40 times 3 minus VH times 4 plus 20 times 2, 4 times 6, equals 0 at point D from the right side. So here I'll handle the resulting force, which is 20 times 2, so the resulting force is 40. So we have 40 times 1 minus VF times 4 plus 40 times 5 minus VH times 6 plus 20 times 8 equals 0. If we simplified here VF and VH from the left side, the rest on the right, and here the same. I already enter it into the calculator. Like this, well, this system of equations is simple, so it can be solved by hand, no problem. And from this system of equations, we calculate the reaction VH, which is 40 kN, and VF 40 and VH 40. And we have it already, so now the sum of moments at joint B also from the right side equals 0. And it looks like this: 40, which is here. This moment, minus VC times 2 plus 40 times 5 minus 40 times 8 plus 40 times 9 minus 40 times 10 plus 20 times 12 equals 0. VC is 60 kN. And the sum of moments at point A. Now, if we did, say, the sum of moments at point B, even though there's a joint, the equation doesn't have to be for the right or left side, it can be for the entire beam, which means we could do the sum of moments in any point for the entire beam. But I've done it at point A, so let's go through this equation. So we have moment MA plus 40 minus 60 times 4 plus 40 times 7 minus 40 times 10 plus 40 times 11 minus 40 times 12 plus 20 times 14 equals 0. There are quite a few forces here, but the numbers come out nicely rounded. Moment at point A equals 80 kNm. There is an error here. And now the last equation we have left, which is the sum of projections on the y-axis, equals 0. Which means all vertical forces, Virginia, plus 60 minus 40 plus 40 minus 40 plus 40 minus 20 equals 0. From this, VA equals minus 40. So the direction of the reaction is not as I initially marked it, but in the opposite direction. And then it will be a positive 40. And so I will write it down with such a direction on the next slide. For the rest of the reactions, the signs agreed with me. And you see, in reality, we don't need these reactions at the joints. Did they help us with drawing graphs in the previous task? They were only needed to transition from the main beam to the sub-beam so that the sub-beam was determinable, so we could calculate it. We needed this reaction at the joint. But for drawing the graphs, they are no longer needed, they are superfluous. In this way, we can do without calculating these reactions. And as I say, there are tasks in which, like in the previous one, I specifically wrote the content in such a way that they ask us to break this Gerber beam into simple beams. So if so, then you also need to know how to break it down. And if it's not necessary, just draw the graphs, then it is not necessary. And there is also less thinking about which one is main, which is subordinate. And it seems to me that this is faster. Well, okay, we have calculated the reactions. We can... I did a check here as well, okay. Let's do the check. I did the sum of the moments at point D, so no reaction passes through this point. And also such a long check because there are quite a lot of forces here. So we have that moment 80, minus that 40 at 6 meters, plus 40 that moment. Plus VC, which is plus 60 times 2, plus 40 times 1, minus 40 times 4, plus 40 times 5, minus 40 times 6. And the last one, plus 20 times 8, equals 0. And you can check it actually equals 0. The left equals the right, so it's okay. So let's draw the graph. I have already entered the reactions instead of VC, VF, and VH that I calculated. And we draw. I will not dwell too much on this. 40 down, then we don't have any shear force. Then we have... Then here too, there is no shear force. There is a moment, but the moment does not affect the shear force graph. So it's still minus 40, then 60 up, so to positive 20. Then there is no shear force, so the 20 doesn't change. Next, we have continuous load. The resultant of this load is 20 times 2, which is 40. So from our positive 20, we move 40 towards minus, which is down, as indicated by the direction of this resultant. So we also see that this graph should pass precisely through the center, from 20 to minus 20. Cut plus minus, then in this section there is no shear force. Then we have a jump of 40, which means up to plus 20. Then we have here... Oh no, I didn't draw the guidelines, you see. Then we move to the next shear force. Here we have a drop of 40 down, which means to minus 20. Then the value does not change, 40 upward. Now it's 20 here on top, and to the end of the beam, 20 down, which lowers our shear force's graph to 0. Plus, minus, plus, and 20. All right, I'm counting the areas. So here we have 40 times 2, which is 80. Now this one, 40 times 2, 80. 20 times 2, 40. 1/2 times 1 times 20, which is 10. 10. Because here is 1 meter, right? This length is 1 meter, because this graph passes through the middle. 20 times 2, 40. 20 times 1, 20. Here it's the same. And here 20 times 2, 40. We are drawing the graph. Is there any external moment on the right side of the beam? No. We have to descend to 0 at the end here. Where else should there be zeros? At the joints. Very important information, very helpful. We can immediately tell we're miscalculating if we don't come down to 0. Here there should be 0 and here should be 0. And at this end, we have a moment of 80. It is clockwise, which means positive, or simply pushing the graph down. This arrow here down. So this is positive 80. So here we start with a value of 80 because we have a moment on the beam. And that's positive 80. Then what do? 80 towards the negative. The value was constant on Q, so on M linear. And the positive value was here. So at the joint, we are at 0, which is nice. Next, we have a jump of 40, because there is this moment, and it is like in a joint but on the right side. As I mentioned at the beginning, the moment must be marked, either on the right or on the left. While shear force can be typically on the joint, the moment must already be defined either on the right or on the left side. So now we have a positive 40, a jump of positive 40. Here we have pluses at the bottom. So in this joint, it zeroed out, but we immediately have a jump. That can also happen. So we are at positive 40, now 80 linearly towards the negative. So we move the graph to the other side to the same value, but negative, 40. Then, so we are at a negative value. Then we have towards plus, because that is the sign of this graph by 40. There was a constant value, so we go linearly here. Well, to the joint to 0, it's okay. Now here we have a linear graph, so we will have a parabola. So first, 10 towards the positive, then again towards the positive, and then 10 towards the negative. So it will be a parabola with a maximum value of 10. 10 plus, you understand. We were here at 0, now the area is 10, right? And it is positive. The shear forces graph here is positive. So first to the value of 10, a change of 10, but here I had it linear, so I draw a parabola. 1 degree higher in the equation, and then I'm at 10. So here we calculate the maximum moment. And now from this positive 10, the value of the area of this triangle. 10. It is negative, well, to 0. From the positive value of 10, a change of 10 by minus 10 to 0, okay. Now linearly 40 negative, so upwards. Then here should be the auxiliary line, 20. We are at 40. Now 20 towards the positive. Linearly, let it be 20 and linear. This is 20, then 20 towards the negative. Also linear, so we return to negative 40. Minus, minus, and we are at negative 40. And now we have a positive area of 40, well, to 0, linearly. All right, we have the shear force diagram, we have the moment diagram. We managed with this Gerber beam. If you think the material was helpful, I encourage sharing it with colleagues. I recommend subscribing to our YouTube channel, file on Facebook and Instagram. And for now, that's all. I wish you pleasant studying. Best regards. Goodbye.